Oh, hello everyone, and welcome back to another episode of AWS OnAir Data Dive. This is the show where we dive deep and get those data treasures for you. My name is Aditya Samant. I'm your host, coming to you live from Dallas, Texas. Now, this is a show where we primarily talk about relational databases. And relational databases tend to be the heart of most applications and organizations. So it's only obvious that people deeply care about the performance of these databases. Usually the faster the database, the faster the application, and that has direct implication on the business, sometimes even generating revenue, getting those orders, and that kind of good stuff. So with keeping that in mind, then today's topic is going to be about performance, and specifically about RDS MySQL performance. Now in this show we talk a lot about Aurora, but today we're going to pivot a little bit and talk about RDS instead. And now to talk about that in more detail, I have my good friends and colleagues, Shagun Aurora and Simon Comendera from the Specialist SA team. Now these two are kind of becoming regulars, but for the folks who don't know, let's get those introductions out of the way. Shagun, let's start with you.
Sure. Hi, everyone. My name is Shagun Aurora. I'm a database specialist solutions architect, joining yet again from very hot Dallas, Texas, where it looks like I'm getting a heat advisory alert every 5 minutes. But thanks all for joining in.
Awesome. Thank you, Shagun. Simon?
Hi, folks. This is Simon Comendera. I'm a specialist solutions architect on the same team with Aditya and Shagun. Joining you from Denver, which is at 66 degrees, very pleasant, probably the first nice day in what seems like an eternity. I'm happy to be here. Only my second stream. I hope to stick around for longer.
Oh yeah, absolutely. You're very welcome, Simon. We love your demos, and I'm jealous. 66 degrees, man, that's amazing. Where is everyone joining from? Let us know in the comments. All right, well, how are you guys feeling today? You feel like dropping some performance tuning knowledge on our customers?
Yes, very excited to do that.
Yeah, and specifically, I think the thing that customers really care about and ask quite often about, like the performance tuning in itself is called kind of an art, right? Like there's the query tuning and the schema tuning and figuring out what the queries are. But we'll talk about some of that. But I think today's focus is going to be what are those features that you can use, that you can just turn on and get some performance boost. And so we'll keep with that theme. But before we get there, Shagun, can you tell us, there's RDS and there's Aurora, right? They both offer Postgres MySQL. Also, RDS offers Postgres MySQL. Why do folks use RDS? Is there any specific reason?
Yeah, no, a lot of my customers do use RDS today as well. So Aurora is definitely the AWS, cloud native database that we built that has multiple improvements in the storage subsystem and a whole bunch of features as well. But I have seen customers who especially want to stay updated on the latest MySQL minor versions. They do tend to choose RDS MySQL. This is where those minor versions are released first, and then about a gap of 2 to 6 months is when those versions then end up in Aurora MySQL.
Yeah, so if you want to stay up to date with the absolute latest and you need that version currency, RDS is going to give you that. And of course, you also get that control plane, right? So you get the same functionality, you get the API, you can take backups, restores using just say CLI calls and things like that. Mm-hmm. So that's all great. Simon, what are some of these features that now we already know, like Aurora has a lot of innovation, but I know we also put in a lot of effort into improving RDS. What are some of the features that you can think of that are specifically important to performance when it comes to RDS MySQL?
Yeah, good point to start, I guess. This is something maybe that the database experts out there take for granted, but obviously this is something where when you're talking about performance, first what you're thinking about is the areas that really determine your performance. What is your performance a result of? And there's usually a few layers that you consider in a relational database that would in the end produce a certain degree of performance, and that is CPU and memory performance. There is the IO and networking stack, as everybody probably can relate to. the I/O and storage performance is probably one of the most significant factors that goes into your query processing speed, especially for the writes, but often for the reads also. So there's those different areas where performance can be influenced, and those are the areas in which we build features in RDS to, help you squeeze the last ounce of performance out of your database in those areas. So, for example, we have for the compute and the memory performance, we have Graviton instances. These are the ARM-based architecture instances that give you high efficiency, good price performance for workloads that are intensive on CPU and memory. For the I/O and storage aspect, we have features like optimized reads, optimized writes. We have features that address the internals of the engine. So basically what the database has to do to actually run those queries for you. In those areas, we have things like the dedicated log volumes in RDS, which accelerate redo versus the table space write performance. We even have features in areas that have to do with the topology of the database. So performance is not just, a simple thing that just happens on a single database. You will have a topology of resources that is what your database cluster is. So things like multi-AZ instances and multi-AZ clusters with either synchronous storage replication or semi-synchronous binary log replication, all those things influence performance in the end. So you can pick and choose which areas of performance you really care about most, or you can just turn it all on and I guess go as fast as the technology allows. But yeah, this would be the summary. I'm sure we'll go through the demos and examples very soon.
Yeah, I mean, that makes sense, right? Like performance usually gets categorized into the compute performance, like you said, processor and memory. And then there's the I/O performance. That is a huge deal when it comes to databases. How much you can offload to the memory, how much you don't, if you don't need to go to the storage, the performance of databases tends to be better. I know we were going to talk about a lot of that. You alluded to the ARM processors, the Graviton based processor. I think while we do offer ARM based processors or the Gravitons, there's also the regular x86. What's the difference there in your experience?
Yeah, so just to do a quick recap, we are talking about the different CPU architectures, ARM-based like Graviton or x86-based. And so these are different sort of instruction set architectures. We're not probably going to go too deep into what goes into each one, but the traditional approach to describe this is that ARM processors are generally more efficient at in turning electricity into performance. And
power efficiency
in the context specifically, power to performance ratio is generally sort of an advantage for ARM. In this particular case, we're also looking at certain advantages for database workloads in the context of the Graviton instances versus the x86 based instances. And the main advantage there is that in addition to having that efficiency advantage, you also have a difference in how we treat the virtual CPUs that you allocate to your database instances. So whenever you're picking a provisioned or reserved instance type for your RDS database, you're going to be picking an instance type that has a certain amount of virtual CPUs and memory. And so the vCPUs are one of the most important factors based on which you're choosing your instance type. And so for x86-based processors, these virtual CPUs are basically hybrid threads. So you have your physical cores and you have hybrid threading enabled on those cores. So a vCPU will be basically a hyperthread. So for physical cores, let's say 8 hyperthreads, that'd be 8 vCPUs. Whereas for the ARM-based processors, the Gravitons, each vCPU is an actual physical core. We don't have hyperthreading for these. So for anything, for two sort of comparable instance types, let's say 2XL x86, 2XL ARM-based Graviton, you have 8 vCPUs that are 8 hyperthreads versus 8 vCPUs that are 8 actual physical cores. So as soon as you start going higher in your CPU utilization, as soon as you start pushing, above 50% CPU saturation, the ARM-based processors will start gaining advantage over x86 because they don't have to use hyperthreads. They have full cores to work with. So probably not a huge deal for someone who's running at 10% CPU, but definitely showing as a big advantage once you go way upwards of 50% CPU utilization.
Awesome. Well, thank you for that very technical explanation. I'm sure folks appreciate that. All right, so enough talk. I think we need to see some demos. And Shagun has some demos prepared for us. Shagun, what do you have in terms of demos for us?
Yeah, sure. So I have two demos for you. One is how easy it is to go ahead and create an RDS instance with all the features that Simon talked about in terms of instance class, storage, and all the other additional optimized features as well. And a second demo is going to be to show you the performance difference, one with a standard RDS instance and another one with all the features bundled on top of each other. Before I get started with the demo for everyone listening in, a very quick introduction to what is optimized writes first. Optimized writes is going to be one of the main things that I'll talk about in the demo. But firstly, without optimized writes, how MySQL writes is as you're making changes, this is all written in 16 KB pages, which is then written atomically in 4 KB chunks, first into the MySQL double write buffer, and then it goes into your table space. So there's an extra step of writing it twice. And the reason we do that is to maintain durability. So in case, obviously, if there's a power outage, you don't lose that write. And the biggest thing with some of these push button things and like kind of improving performance is that you do less so that you improve on performance. And that's exactly what we do on the right side of the screen. Once you do have RDS optimized writes enabled, what happens then is that as you are pushing writes, this is all atomically getting written into your table space directly. And this is written durably as well, so that it saves you against that power outage. How we do that is with the help of AWS Nitro systems that have torn write prevention inbuilt into them. So we are able to write once, but write it durably. And because we are removing that double write buffer from the mix, you can get up to 2x faster performance, especially for workloads that are very write heavy.
Yeah, very aptly named feature of MySQL double write buffer. You're basically writing everything twice. Well, not everything, but quite a bit. And I know that this is some of these databases, when they're built back in the day, hardware was not always reliable. So you had to put in an extra effort from the software side to actually take care of something in case you lost something, so you can always recover that database. So now we essentially have the ability to take advantage of the modern hardware, and it's and just kind of short circuit these writes directly to the storage. So that makes a lot of sense.
Yeah.
All right. So yeah, do less and achieve more. I think who wouldn't want to do that?
Yep.
All right, so let's see how easy it is to add stack all of these features on top of each other.
Yeah, sure. So first, when you're creating your database instance, so today we are going to focus on MySQL on RDS. Now here with the optimized writes, you do have a toggle button that you can push so that it just kind of enables the versions that are going to support optimized writes. This is going to be MySQL 8 onwards. And then you can go ahead for this purpose, like for the demo that I've created, I'll be showing it on a multi-AZ DB instance, which is what customers typically use to get the high availability use case. And then you can provide an identifier, username, password, all of that. But with the instance configuration, so like I said, this torn write prevention is built into the AWS Nitro systems. So in this case, this is again a toggle button that you can use so that it only shows you instances that supports optimized writes. And this is not just the Graviton instances. You'll also be able to see some older instance classes that customers may already be using, like some of the x86 ones. And they also support the optimized writes feature.
I guess the instances that have the local storage, local SSD storage, can use optimized writes.
Mm-hmm. So with this, you can, choose the instance class that you want now. And this is again, like we said, so not just a difference between what supports optimized writes versus what doesn't support, but like Simon was mentioning in terms of differences between x86 and Graviton processors, this is also where customers can make that decision, choose a Graviton instance to get some of that price performance benefit that comes with it. In terms of storage now, for customers who have been on RDS for several years, they know that we used to offer 3 types of storages back in the day: magnetic, and then there was general purpose, which we called as GP2, and then there was IO1. A few years ago, we started support of the latest generation in general purpose called GP3. And very recently, we have also added support for IO2 now, which is the latest generation on provisioned IOPS. And how this helps customers is, again, using the benefits of that hardware and some of the changes that we have made to the volume itself to give you the highest kind of durabilities, at the same time give you very little latencies, and kind of avoid some of the jitter issues that customers may have seen when they're using RDS. Another very cool thing about IO2 is, first, it's not priced differently. So let's say if you're using IO1 today, and I think it becomes a no-brainer to get to IO2 because storage is built the same, and then your IOPS are also built the same. Another cool thing I like about IO2 is the ratio between the storage and the IOPS. So back in IO1, it used to be almost like 1 to 50, and in this case, it's 1 GB to 1,000 IOPS. So really, it gives customers the ability to right size on storage. And let's say if they don't require the storage, it's more an IO-intensive application. IO2 does make sense to give you that performance and then give you the ability to right size as well.
Yeah, makes sense.
All right, so this was on the storage part. Now, dedicated log volume. Simon touched on it, but this is, adding another volume, which kind of stores all your transaction logs, keeps your data separate, which is ultimately going into the EBS volumes. So we are able to reduce contention and then again provide benefits in terms of performance. This feature is supported actually for MySQL, MariaDB, and Postgres on RDS. And like you see on my screen, it's again a simple checkbox that you can enable. And with all of these things that I'm talking about, it's not just on the creation page that you will find them. You can very easily go back and modify existing instances. Yeah. So with a lot of these, actually, they don't even require reboot. With dedicated log volume, there will be a reboot required as you're turning it on and off.
Yeah, because you're probably moving the data from one volume to another. And the dedicated log volumes is probably a fancy name, but it's an old DBA favorite I remember from back in the day, where you want to isolate the sequential writes of logs on its own drives, and then the random access of the data in its own drives. Funny enough, in the data center environment, sometimes those logical volumes will be carved from the same physical volume, so they end up in the same space anyway. Thankfully, that's not the case here, so we should see a significant performance improvement.
Yeah, that's true. But yeah, so this is everything, the rest of the piece doesn't really change with respect to networking and monitoring. So what I'm going to do now, like for the demo, like I said, I'm going to have a standard instance class and then compare performance with an instance class that has all these features enabled. So let me go ahead and get started with my Sysbench. So what I've done here is with Sysbench, created about 50 tables with 1 million rows in each table. And I'm only going to run, the write-only workload over here. So the right side of my screen is running the optimized version. The left one is running the standard version. So you can see there's two different endpoints. One is RDS Lab Standard, and then the other one is, the optimized one, the right optimized one, pushing 1,000 threads for 300 seconds, which is 5 minutes.
Live demos.
Mm-hmm. Yeah,
Did you pray to demo gods?
No,
demo gods,
hope.
please. Okay.
Yep. I hope this goes well. But okay, let me show you how I set this up. So these are the two instances. I'll show you the optimized one first. So to kind of make it consistent, both the standard and the optimized, they are both on 16 extra large. So it gives you the same vCPUs in the memory. And the only difference here is I'm using a Graviton instance class versus an x86. Another one that I've added here is IO2 volumes to show improvement with that. Yeah. And then on the dedicated log volume side, as we can see, it's turned on.
So several of these options are stacked on top of each other here. Okay.
Yes, yeah. And comparing it to just my standard 16XL, it's going to have IO1, the 6,000 same IOPS on here, and then no dedicated log volume that's enabled. And because I wanted to, so this is again, like I was saying, customers can tweak some of these things. So with optimized writes, if you want to make sure that, these are turned off, which I wanted to do that for this particular demo. So in this case, you can, it's a parameter in your parameter group. You by default it is set to auto. So if you use an instance class that allows for optimized writes, it's going to be on by default. But you can set it to off as well. So that's what I have done with the standard instance class.
And optimized writes by itself has no cost, right?
Yes.
So there's no reason why to not use it.
Yeah, no, definitely. And that's just, coming back to the AWS promise. We really don't charge you on the basis of the features that you're using. It all comes down to the usage in terms of resources and the hardware that you're using. Okay, so these are my two RDS instances. I'm going to now, I have performance insights open for both of these. So this is going to be the optimized instance. I'm looking at the dashboard for, the last 5 minutes. And we do see, all of this load piling up on it. If I compare my I/O throughput, in this case, it's spiking up to 32.8 MBs. And these are just some additional metrics that you'll see because this has that the dedicated log volume turned on. So that's why you'll see additional metrics come up over here as well to show you how that's getting utilized. And then if I compare it to my standard 16XL and then go into metrics here. Okay. So like on the other side, my I/O throughput is about 32 MBs. In this case, it's 29. So we see that clear difference on standard instance pushing
almost 10% difference there
as compared to that. And then there's a latency difference as well. I know it's not very clear over here, but once the suspense output does finish, which almost it's done because I was running it for 5 minutes. I just have to wait for it to come back up. But performance insights is another tool which we'll cover on today, how customers can view it and look at performance to tune it. But meanwhile,
I was going to say, just for the folks who may not have used some of this tooling, this is available out of the box for for all RDS and Aurora database engines. If you use it for 7 days, there's no cost. So it's pretty feature rich, and we continue adding more and more features to it. So this is pretty fantastic.
Yep. All right. So meanwhile, we've the output is done over here. So like I'd mentioned, this is going to be the optimized one. So this is the right optimized one. And okay, you can see the difference in terms of transactions per second. This is pushing 5,700. This is pushing more than 5,900, almost going to 6,000. You see the difference between queries per second as well. 34,000 versus almost 36,000.
1,000 more queries per second. Amazing.
Yeah. And then in terms of latency as well, you see the minimum latency almost cut to half. The average is lower. The maximum is lower. But this is again all those features that we talked about. How easy it is to set them up. There is no cost to set them up as well, and how it can help you in improving performance.
Yeah, and this is something that customers ask quite a bit. What are those? Can you tell me a silver bullet? Can you give me some option that I can just turn on that's going to help me with performance? So these are some of those options. And that's, of course, this is a synthetic workload. So in real life, depending on your workload, the performance difference may be more, maybe less. But we're just trying to demonstrate here that the difference is there.
Yeah. Yep. That's it. But yeah, that was all for my demo, showing you how to create, modify existing instances, and then the performance differences with write optimized mainly and the dedicated log volume turned on.
All right, we're gonna, thank you for those demos. That was really interesting. We're gonna move on and talk about some of the availability options and how we go, how we have added some performance improvement there too. But before that, I think it's important to mention to make sure to take our surveys. Hopefully you'll see the survey link here flashing a bit. It's also in the comment section. And the first 50 people get $20 in credits. So take advantage of those credits. See some of these options. Maybe build some cool demos in your AWS account. So take advantage of those $20 in credits. So there's the link going on your screen, scrolling by. All right, so now that we've talked about surveys, let's move on to the next section of our session here today. Simon, I know we have added even more features in terms of availability. So the multi-AZ or MAS availability has been there for a while, but there are some additional feature additions in that section too. Let's maybe talk through those.
Yeah, and here's the thing. In reality, as much as it's nice and convenient to just focus on hyper optimizing a single database host and turning all the parameters up to 11 to make it go as fast as possible, in reality, there's other considerations that you have to take into account. So if you're setting up a production database, and DBAs running MySQL out there will probably relate to that. You can't just turn every parameter up to the maximum value. It might, compromise stability. Some things like the redo log size and the buffer sizes and all that stuff needs to be sort of tuned, but it needs to be done carefully, because otherwise you're risking, exposure anywhere from, crash recovery performance to stability to begin with. And then there's also the aspect of the topology of your database. You're probably not running a single host with an NVMe on it, and if it blows up, there's nothing you can do. You're probably running a topology with some sort of replication, be it storage level or logical level with bin logs, and that will also slow you down potentially if you don't have really good plan, in place as to how to find really the sweet spot performance versus all the other considerations. And so that's where the different multi-AZ sort of layouts come into play for RDS. And I can just real quick run through that here. The multi-AZ DB instance configuration that probably anyone who's ever used RDS MySQL is familiar with. It's been there since, feels like more than 10 years now, since forever. And that's the configuration we have here on the left side. This is basically a pair of instances with a primary active instance and a standby instance in another availability zone. The standby is a cold standby. It does not actually have MySQL running on it. It's just waiting there, ready to take over. And then there's two separate storage arrays, EBS-based, under each instance. And this replication of changes of data happens at the storage layer, and it's synchronous across those two AZs. So basically what happens is when the primary goes through its write path to write something to the storage array, that gets synchronously replicated to the other storage array at block level, and it has to come back, the acknowledgement has to come back before the primary database goes back and acknowledges the commit to the client. And so that's great because you get, basically synchronous replication. So if anything goes wrong on the primary, you can assume that the data, anything that was promised, committed to the client, already made it to the secondary. The drawback here is that, like I said, the standby instance is a cold standby, which it's there, but there's no MySQL running on it. So what happens when the primary has some kind of issue and we need to do a failover to switch the primary role to the other AZ, we have to actually bring up the MySQL process, start it up on the secondary node. And what that means is you have to go through all the crash recovery in MySQL, depending on your workload, depending on your data layout. It might be very quick or it might not be very quick at all. And a good example of when it might not be quick is, something like a software as a service, multi-tenant workloads with 100,000 tables or 1 million tables. And InnoDB has to go through all the song and dance with table space discovery, recovery, checking that the page headers are fine and all that stuff. And it can take many minutes if you are really looking at something like I said, many tables and under heavy load. So that's, there's something that's great about it, something that's not so great depending on your workload. And so that's where the new model, which we call the multi-AZ DB cluster, comes in, which is a second option that you can choose from. And that model uses 3 instances in 3 different availability zones. There's still one primary that you can write to, but you have 2 readable secondaries. And instead of doing storage layer synchronous replication, we're using MySQL binary log semi-synchronous replication. So not only that, we're also putting local volumes. We're using instances with local storage volumes, basically the EC2 instance store. so that when we're working with logs, as far as the write path is concerned, when we're writing to the logs, we're writing it locally on that local volume, and then we use semi-sync replication to push changes through bin log to the secondaries, and we use EBS underneath when the data is written asynchronously to EBS. So you get a quicker response from the log writes, and you then push it to the secondaries through asynchronous replication. But as I mentioned, and the critical part here is that those standby instances are up and running and readable. They have MySQL running on them. It's up and running. Obviously, needs to be the case because the logical replication is between running MySQL servers. So what's great about that is not only do you get faster write path performance due to the local, writes for the logs and the immediate commit, but also when you're doing a failover, when we do a switchover between those instances, we no longer have to actually go and bring the MySQL process from zero and you do crash recovery. The MySQL process on the secondary can just take over without restarting. And that is a tremendous advantage here. And so, you can actually, it can potentially cut your failover times down, by an order of magnitude if you're running something like a million table system or something that has heavy load and a huge redo log that would normally take a long time to process during crash recovery. And we can put a demo here just to show you how quick it actually is.
Yeah, let's see the demo.
Let's do that. And it's a live demo again. So
demo gods, please.
Possibly go wrong. Yeah, so what we're going to do here is we actually have a couple of databases here.
Yeah.
Oh, I'm going to be typing live, which is even better. So we have instances with 100,000 tables in them. Run-of-the-mill multi-tenant system. You have these are dummy tables, but it's the numbers that matter. So what we're going to do is we're going to try to see what happens if we try to fail over those databases simultaneously and see what kind of improvement we get on something that has to go through crash recovery versus something that doesn't. So on the left-hand side, we're going to start pinging our multi-DB instance. So this is the traditional storage level synchronous replication. And on the right-hand side, we're going to start pinging in a similar fashion our multi-ZDB cluster with logical replication, the one that does not have to go through crash recovery, and fingers crossed, does a much better job here in terms of the failover. So what we're going to do now that we're pinging those two, we're going to go into our database console and basically get a failover going. The failover won't start at the same exact time because we're doing this through the console, so there's going to be a delay as I am clicking here. So the multi-ZDB instance, that's the traditional one. We're going to do a reboot with a failover, have it go there, and then for our multi-ZDB cluster, we're going to do the same. We're just going to do a failover here, and boom, and that's all we need to do to simulate the failover. And in just about a few seconds, that failover should, it's already kicking in. We're starting getting errors. I'm going to need you guys' help with the math here because we're tracking the timestamps here. But on the traditional multi-ZDB instance, we're starting our failover. So we're starting our downtime window, basically 33:19, more or less. Let's see how long until it comes back. And then we're going to do the same thing on the multi-ZDB cluster. Yep, there we go. So because I needed a few seconds to click around, the multi-ZDB cluster started downtime at 33:44. Let's see what happens there. So momentarily, we should just start seeing this come back to life. And I'm right.
Yeah, I'm sure you are. There we go. There we go.
Not so bad. So again, this is the multi-ZDB cluster, the one that has readable standbys, did not have to go through crash recovery. And as I'm rambling on, the one that does crash recovery is still, doing its thing. So this was what, 33:44, 34:08. So yeah, it was like, 20 seconds?
20 seconds-ish.
24 seconds to do recovery. And again, this is not going to be proportional to like what you're doing on the database either, because we're not doing crash recovery. So if it had 500,000 tables on it and workload running, it would have been the same time ballpark, right? So that's, hopefully the other one also goes back.
Wow,
I would probably expect something in the order of 2-3 minutes. And the important thing is that the predictability of this process is a value on its own. There we go.
Yes.
33, 34. Yeah, it's like 2 minutes or so.
Yeah.
So the thing is, if this was the crash recovery case, you have to always be mindful of what you're doing with your database, right? If your data set keeps growing, your workload keeps growing, this process will get longer and longer as your application gets more and more, uses the database more heavily. So the predictability of the recovery process here is a concern versus on the multi-DB cluster, you basically get predictable failover times, which are not nearly as dependent on how you're using the database. So it's not only the performance of recovery, it's also the predictability and sort of the peace of mind that it's not going to change much, even as your application grows. So yep, that wraps up the demo, I think, for this one.
Yeah, that was a great demo. The predictability piece is definitely something super important for our customers too. And, I would wager if we give an option to customers, something that is somewhat faster versus something that is always predictable, a lot of customers will select the predictability over, unpredictable fast performance almost.
Yeah, and it's not like you're giving up performance with this either, because multi-DB clusters also support those advanced, storage types, IO2, which is quite exciting indeed. It's not only an optimized protocol, but it's also actually dedicated hardware on the Nitro hosts that give you basically sub-millisecond latency. So it's not like you have this or the other. You can enable the cool storage features and stuff like that on multi-DB cluster also, while also having this more predictable recovery.
Cool. Okay, so we saw write performance improvements live demo. Well, you just showed us performance improvements in recoverability and availability of the database. I think the read performance needs a demo too. What do you say, Shagun? I know you have a demo ready for that. And, typically we have the ability to get more read performance by just adding more readers, right? So in RDS, you can add more readers. I think in region, you can add all the way up to 15 readers. And sometimes you can actually do you can stack the readers on top of each other. So you can achieve that read performance just by scaling the readers out. But it's also nice to just boost the read performance directly. And I think that's what you're going to demonstrate.
Yeah. So the feature that I'm going to show right now is very similarly named to optimized writes. This is called optimized reads. Hopefully it does exactly that in this demo. But for my previous demo, I used Sysbench. In this demo, I'm going to use MySQL Slap, which is a load emulation tool. Typically, I see customers, feed in their general log or slow query log files to MySQL Slap so that it runs. In my case, I'm using it to run a select query, which is not indexed. And the table on which it's going to run has 10 million rows on it. So we're going to see how that works. Now, this select query does use group by, order by. So it is going to create temporary tables, which is essential for my demo. And I'll talk about why it is essential. But I'll go ahead and start this over here and see, we are again comparing how fast it comes back. So the right side of my screen, the host here is MySQL read optimized. That is my endpoint. And on the left side, it's just MySQL read standard. And while this is running, let me just talk quickly about what this feature is. So the left side of my screen, I'm still on the optimized write slide. Let me get to optimized reads. So that's this slide now. So on the left side, how this happens, like on a typical MySQL, is if you are running complex queries that are generating temporary tables, once these temporary tables grow in size, which is customizable through a parameter, but once they do grow in size, then they are moved into the disk storage, which for RDS is the EBS volumes. And what that means is that you're writing into that EBS volume and then reading from that temporary table on that EBS volume as well.
Yeah.
And now compare it to with optimized reads, what happens over here is that right now with optimized reads, we have introduced up to 2x faster query processing. And it's again the same strategy of do less work. And how, what happens over here is these are again Nitro instances, specifically the ones that have NVMe storage, or we call them instant stores, attached to them. so that as your temporary table size grows, rather than going and putting it into an EVS volume, we put it right next to your host in that NVMe storage, which gives you those improvements in query performance.
Yeah. So I mean, instead of having to travel, EBS is basically network attached storage, right? So you have to travel all the way to get to the store. Here, the NVMe's, I think there is, I forget the name of the technology, SRIO, I forget what it is, but it's almost like they're right next to your processor.
Yeah.
So it's just much faster for you to read and write to them.
Yeah. So with these queries, and that's why, in my demo, I said I'm using that kind of a query, which generates temporary tables. So for folks who want to use this, if your workloads have sorts, hash aggregations, high load joins, common table expressions or CTEs, or even queries that you may be running on unindexed columns, because, we cannot just ever get around adding the right indexes and whatnot. So that's where you're going to see improvements.
Or even building indexes. Right, creating
Yeah.
indexes itself takes a
on a
long
larger
time
table.
because it requires
Yes.
the temporary store.
Yep, that's true. Okay, so let me see what's going on. All right, so on the read optimized side, we see this is already finished. Hopefully this comes back over here soon as well. So this took around 45 seconds over here. If I have to give you a sense of how it looked like on Performance Insights. So I have my read optimized. We see that the load here ran for just like that 45 seconds. Whereas if I compare it with the read standard, this is where I see that the query is still going on. And to again show folks that there's nothing fishy over that's going on. The only change that I have between read optimized versus the other one is the instance class. That's the only thing. So with this feature, this comes on by default. So if you're using an instance class that supports read optimized, it's going to be on by default. So in terms of configuration, I'm using IO1 500 GB 4000 IOPS. Compare it to my standard. So really I'm using the x86 instance class by using the same IO1, no dedicated log volumes, none of those things are turned on. So this is purely based on that, the read optimize and how it's looking at, the queries. The one more thing, customers, especially when they're looking at read queries and they want to, have a look at some of these things. So while, some of these queries are running, this is where you can come into, that top SQL statement, look at rows examined versus rows sent. That's a very typical MySQL, concept that we use to try to see how many rows the application is sending and how much the explain plan is looking at. But if I go to my Cloud9, this has also completed now. And that's basically
Quite a
the
difference there.
Yeah, between the two of them on reading these queries.
Almost 5x, almost.
Yeah, yep. And so because with this one, it's unindexed running on a 10 million, data set, 10 million rows data set. So that's why I just, ran it with a concurrency of one thread. But this does amplify, when you put more threads at it, run it for more iterations. So that can be, things that the customers can try on themselves as well to see how this changes.
Yeah, that makes a lot of sense. I mean, just taking advantage of that local NVMe, anything that spills over on temp tables, this is, again, one of those options. It's just all you got to do is enable that option and enjoy the benefits, right? There's no query tuning or tweaking there. It's just by the virtue of having that local faster storage available, you get that performance benefit. Well, excellent. Well, thank you, Shagun, for this demo. I know one thing that is also important in performance is caching. So we talked about the compute and memory. We talked about the NVMe and its advantage, and it's kind of sort of works as a cache layer between the memory and the storage itself. But Simon, what's your thoughts on other types of caching that sits on top of the database, and can sometimes turn those millisecond queries into microseconds? There are customer workloads that are highly dependent and very sensitive to query latencies. What can we do in that area?
Yeah, or better, turn those multi-minute queries into milliseconds. If that's what you're after. And this is a good question, especially now with basically no built-in cache for query results and the newer versions of MySQL. you're going to be looking for options out there. So caching is probably something that everybody knows about, but if you actually go and try to implement it, it might not be as trivial as you had hoped. So it's it's a good way to accelerate query performance basically by not having to run queries. That's all there is to it. If you can store results, even partial results, for whatever is needed to build the website or to give the result back to the customer, that is a valuable thing to do. And there's basically, two ways of thinking about this. For applications that have pieces of data that they need from the database, but they don't change very frequently, such as, I don't know, if you're running an e-commerce application, you have product descriptions, or maybe you have comments for product or reviews that once posted don't really change. Anything that is written once and read millions and millions of times, caching those kinds of pieces of data in the application layer is probably a very efficient option. So typically you would put some kind of a middle layer in your data access pipeline in the application. So if you're reading through an ORM, or if you're reading directly from a database, you can just try to get a cache hit first from something like Elasticache. We have AWS Elasticache, which supports multiple key value and memory storage engines, which you can just call the API from your application, see if the data is there. If the data isn't there, go run a query. And usually those key value storage options, such as the ones we support in Elasticache, would have built-in functionalities that actually reduce the amount of work you have to do in the application to the minimum. So, for example, those databases would have support for time to live for content, so they automatically expires. You don't have to worry about expiring that content. They have support for different data types, simple text payloads, or maybe something like counters, or maybe lists, stuff that is typically useful in an application like that. But you don't have to run the implementation itself in the app. You just use the API of that key value database. So that's a great way to deal with something that is a piece of data that changes rarely, but is read frequently. It's not always that simple, though. Sometimes you have queries that are either so that they're varying to the extent that you can't cache them, or maybe you can't afford to have a stale cache because it's a client story that the queries run in sequence have to see the most recent data, or else the results are incorrect. And for that, you will probably need something like a protocol level cache, or basically cache on the wire. And although we obviously are not suggesting or recommending any particular solution here, but there's solutions out there for on the wire caching for MySQL. If you can look for those out there. Basically, you would be looking for either something like a protocol cache or cache on wire. You'll find options out there. The idea is that there's basically like a middle layer, not in the application itself, but in between the application and the database. So kind of like a proxy, not exactly, but kind of like a proxy through which you push your queries, and the caching service can figure out, or you can tell it what you want to cache. And the invalidation of the cache is also handled through that same protocol. So whenever you're caching a piece of data, but then you're modifying that, let's say that table that you cache the results from on another query, the protocol cache will automatically pick that up and it will automatically invalidate the cache. So the application doesn't have to worry about having stale reads. So these are the two main ways to do it. Of course, if you don't want to run, you don't want to run a middle layer in between the app and the database, that's understandable. Although, again, there's different use cases for different types of caching. So it's not like you always have to pick one over the other. It's perfectly viable to run a hybrid system where you do something in Elasticache and something on the wire. Or you can build your own cache, in which case you're probably going to cry in 2 months and just give up and do something else. The cache coherency and cache invalidation is a hard problem to solve. So the recommendation, I think, from our side would be look at what is available out there before you go building your own cache, because it's just not trivial to do.
Yeah. There's a very relevant question from Strauss Vandor. You need to make applications work with Elasticache, right? I mean, you have to, if you're going to use something like an Elasticache layer on top of your RDS or any other database, that means your application has to be aware of that cache. It's not just simple, like it's not like adding additional buffer pool and then you just connect to that buffer pool and everything is good. Your application has to actively know that there is a different layer of cache, and it has to make those active decisions of how to interact with that layer.
Yeah, you do need some degree of awareness. So like I mentioned in the beginning, for something like, let's say, a product description, you would have a one step in front of actually asking the database for the data. So you would go ask the Elasticache API, give me a payload for product description ID XYZ. You either get the result back or you get a cache missed, or there's no cache available. And if there's no cache, you just go, you sort of pessimistically switch to the database. But if there is a cache, you just serve it from the cache. But that does require application support. There are definitely like application frameworks or ORM frameworks out there that would have caching abilities built in. So it might also be the case that you don't actually have to build everything from scratch, but your framework, your ORM, or your third-party software stack actually has support for that already in it. So it's not necessarily the case that you have to build the code from nothing.
Yeah, makes sense. All right, so I think there's a part of whole performance tuning that we didn't necessarily touch on a whole lot, which is actually diagnosing and finding where the performance bottleneck is, right? So we talked about a lot of features that you can essentially just turn on and enjoy the benefits. But what if you wanted to go deeper and you're like, you know what, I need to figure out where this performance bottleneck is. I need to find out those exact queries and start to tune them. So Shagun kind of showed this feature, kind of touched upon it a little bit, but I think we're going to see it a little more before we conclude. So let's talk about that.
Yeah, no, folks, you already got a view of it. I know a lot of my customers use this and they like the feature. This is Performance Insights, has, like we mentioned early on, has been available since inception of RDS Aurora, and is a free tool up to 7 days retention. And like I was running in my previous demos as well, as load is subjected on to the database instance, this is an auto refresh dashboard that keeps on changing with it. And now, when folks are trying to understand where is that performance bottleneck is coming from, this graph comes in handy. And there's two ways to look at this graph. One is, if I go into some of these wait events and try to see what's actually causing the bottleneck. The other is a more simpler way of looking at, these bars that are coming up. So this dotted line basically represents the vCPUs, right? The CPU cores that you have. And in this case, my workload is pushing way up for what I've provisioned. So when I look at some of these graphs, customers have two options now. Either they start looking into their SQL queries, right? Try to tune them, which you can do from clicking on top SQL. So in this case, there's some update and delete and commit and inserts, all of that, running together. So you can start looking into this particular update query and, try to optimize by that. Or in this case, how I also like, customers to think of is you can do that, but we also have to be conservative about, the hardware that you're working with. So at one point, you may actually have to increase the instance class to, have the query run faster. So that's always going to be a decision that you take looking at this, this metric and also some of the queries that come out of here.
Yeah, no, this is great. And I mean, some of these tools are so handy. So again, without trying to date myself, I'll tell you that when I used to be a DBA back in the day, people would come to me and say, hey, we had this performance issue, and the performance was horrible last night at 1:30 a.m. I'm like, sorry, I can't really help you there because I wasn't there, and we don't have any way to actually tell you what happened. So I'll maybe start some diagnostic, and that performance issue has to happen again, and then we can capture it, right? So to compare with that situation, like this thing is always available. It's free of charge. It's capturing data for you and keeping that 7 days of rolling window at all times. And if you have those issues and someone comes to you and says, there was this issue, performance issue at that time, you could just go there, zoom in, tell exactly which queries caused the problem, what was the wait type. This just it's just amazing. So performance insights along with CloudWatch, it's a lifesaver for the database professionals.
Yeah. And so, like I said, with these kind of, like if your dashboard looks like this is where you can look into either query tuning or, moving into a bigger instance class. But then when I ran that MySQL slap workload, for example, that was just like one query running. I was running it against a table with 10 million rows. So you see the load was way smaller than what I had provisioned my instance class for. Obviously, that does not mean that the performance was quicker. We saw that it took on a standard instance class, some 250 seconds to complete. So in this case, also performance insights, you can see that query, but it does give you all of these other options that you can examine. So in this case, like I was saying, looking at rows examined versus rows sent. So if I click on rows sent per second, this is, by the way, all coming from InnoDB. So you can find that if you run queries like explain, even in your slow query logs. So when you click on confirm here, ideally, what we're trying to do is this number should match that rows examined versus rows sent, or not match, like bring it closer. In this case, like I'd said, there's no indexes. So this is doing a full table scan. But this is another way for customers to kind of look into, is my query already optimized? And do I need to improve my instance class? Or like in this case, you first should look into the query before you start changing the hardware.
Yeah, and the good thing about this is this can be helpful if you know nothing about MySQL or if you know everything about MySQL. So like, even for someone who does not know what these wait types mean, you're still going to get an idea of, is it CPU or is it IO, right? So then you can go enabling those features that we demonstrated, and it's still helpful, right? You can still sort of try to get better performance. But if you know everything about performance schema and all the weight classes are perfectly clear and obvious to you, you have them right there. So you can see, that's just, contending on this or that or index or AHI or whatever, or bin log. So this tool, sort of the same view, can be helpful for someone who is, coming to MySQL fresh, as well as someone who's been looking at performance schema for 20 years. So don't need to be an expert to use this.
100%, right? Like, and the beauty of this tool is that this is available for all engines. So once you kind of understand this tool for MySQL or any one of the engine of your choice, if you're using RDS or if you're using Aurora, you can use that same learning for all of the engines. So, it helps you with other database engines too. So absolutely, 100% agree with you there, Simon.
Yep. So in addition to just performance insights, a few other things like Simon mentioned, looking at performance schema, slow query logs is another thing that customers can enable on their RDS instances. Does not cause a lot of performance, kind of affect performance too much, as long as you're tuning the threshold for it. But slow query logs is going to be another of those things that can help you. And then you can, use that slow query log, put it into tools like PT Digest to be able to understand what indexes I should include, and do all sorts of things to then start looking into your query design and schema design.
Yeah, so you are able to do the things that you can do with your community, MySQL and the community tooling and all that kind of good stuff. That's great.
Yes.
All right. Well, I think we're getting very close to the hour mark. So there you have it, folks. We talked a lot today about performance, the features, the functionalities, the tooling that's available. Again, thank you, Shagun and Simon, for your insights. This was very helpful. I hope everybody found it very useful. I just wanted to remind everyone about the survey. Don't forget to take your survey. Again, first 50 folks will get $20 in AWS credits. So take advantage of that. We run this show bi-weekly. So next show is on August 15th, and we're going to talk about our NoSQL folks are going to talk about OpenSearch. So don't forget to tune in and learn a little more about OpenSearch. Thank you, everyone, for your time, and see you next time.
Thanks, all.
Thank you.